Does this need to have an earth electrode? We get asked this all the time, especially with buildings like this. Garden offices, studios, outbuildings. This one is a timber framed, largely non-conductive, and at first glance it feels like an easy decision. Many electricians would instinctively say yes and drive a rod in. It feels safer, it feels straightforward, and it feels like it covers all bases. But BS7671 doesn't work on instinct or habit. Whether an earth electrode is required depends on the installation itself, the location, and the protective measures in place. In this video, we're going to work through that properly, using real testing on a real installation, and applying the requirements of BS7671. And by the end, we'll come back to this building and answer the question clearly: does it need an earth electrode? What do you think? Let me know in the comments. Oh, and did you know that this video is available as a free CPD? You can head over to Train Essential where you can bag yourself a certificate. I've left links in the description. In many installations like this, electricians will instinctively install an earth electrode. It feels like the safest option, and it avoids having to think too deeply about the installation and the existing installation. But BS7671 doesn't work like that. It requires the earthing and protective measures to be appropriate for that installation. We need to determine what BS7671 actually says, and understand what testing can actually prove. Before we get into testing, it's worth reminding ourselves why we use earth electrodes in the first place. It provides a local connection to earth so that fault current has a controlled path away from exposed conductive parts. In a TT system, that earth electrode is the only intentional connection between the installation and the ground. And that matters because not every earthing system behaves the same way. On TN systems, the earth is provided by the supply network. On TNCS systems in particular, earth and neutral are combined in the network and separated at the point of supply. That works well in most domestic and commercial installations, but exporting a TNCS earth is not always recommended. If the combined neutral and earth conductor in the supply network is lost or damaged, exposed conductive parts connected to the system can rise towards a dangerous potential. This is why BS7671 and other guidance restricts the use of TNCS systems in certain installations. Street furniture, outdoor metallic structures, locations where people can be in contact with the ground and exposed metalwork at the same time. In these cases, exporting the supply earth can introduce more risk rather than reducing them. So this is where we use a TT. By using a local earth electrode, the installation is no longer reliant on the supply neutral for fault clearance. Instead, fault current is limited and controlled through the earth electrode and protective devices, typically RCDs. That separation is the reason TT systems are used in specific scenarios. Street lighting columns are a good example, so are hot tubs and outdoor pools. Some EV charger installations also use a local earth electrode. In each case, the common factor is contact with the ground and accessible exposed conductive parts. The earth electrode helps control touch voltage if something goes wrong, but installing an earth electrode is not risk-free. Driving rods into the ground can bring its own hazards. Underground services, gas, water, telecoms, existing cables, which is why alternative earthing solutions exist. One example is a conductive earth disc system. These provide a large surface area in contact with the soil without the need to drive a rod deep into the ground. They can be installed closer to the surface, reduce the risk of striking buried surfaces, and often achieve very low resistance values. They are particularly useful where ground conditions or site constraints make traditional electrodes impractical. We are going to come back to performance and values later in the video. Okay, so what about the testing side of things and those maximum values that we need to adhere to? When we install an earth electrode, BS7671 does not ask us to guess whether it works, it asks us to verify it by testing. And there are two different tests that we can carry out: earth electrode resistance testing and the earth fault loop impedance test. They are related, but they are not the same thing. Earth electrode resistance testing tells us how well the electrode connects the installation to the ground. It gives us a resistance value, often referred to as RA. That value on its own does not tell us that the installation is safe, but it is a critical part of the picture. BS7671 links the performance of the earth electrode to the protective device being used. In TT systems, this is usually an RCD. In many TT installations, a time-delayed Type S RCD is used for fault protection. This device is there to deal with earth faults and provide the disconnection required by BS7671. Downstream of that, we often use 30 mA RCDs or RCBOs. Those are not there for fault protection of the installation, they are there for additional protection. And that distinction matters because the performance of the earth electrode is primarily linked to the RCD providing fault protection, not the devices providing additional protection at final circuits. Understanding which device does what job is essential when we start looking at test results and maximum permitted values. And we are going to come back to that later when we start putting real numbers against this installation. So that was earth electrode resistance testing, so now it's time to look at earth fault loop impedance testing. An earth fault loop impedance test confirms that the fault path is effective enough for the protective device to operate within the required time, and it's important that we carry out both tests. Okay, so we're back to this installation and back to the original question. Does this studio need an earth electrode? Well, first let's look at what we're dealing with. This is a timber structure. It's mounted on concrete plinths with a timber floor and a timber frame. There is no structural steel connected to the ground and no buried metal surfaces entering the building. Inside we do have metal accessories, sockets, containment and a short run of MICC, but all of that metalwork is part of the electrical installation. It is not an extraneous conductive part with an independent connection to earth. So from an earthing point of view, this is a non-conductive location. The supply to this office is taken from the main installation, which is a TNCS system. And providing that earth remains effective, BS7671 does not require us to install a separate earth electrode for this installation. So exporting the PME in this situation is permitted. Now adding one here does not make this installation automatically safer, but it would make this video a whole lot duller as I need to show you how to test one, apparently. The earth rod we are using here is 2.4 meters long. Under ideal conditions, the current probe would be placed 10 times that distance away. That would be around 24 meters. On this site, we do not quite have that space, so we place the current probe as far away as possible, which in this case is about 20 meters. The potential probe sits between the two at 62% of the distance between the earth electrode and the current probe. That places the potential probe at around 13.4 meters. We take the reading and record it. Next, we move the potential probe closer to the electrode to 52% of the distance. That's 11.4 meters from the earth electrode. That gives us a second reading. Then we move the potential probe further away to 72% of the distance. That's 15.4 meters from the earth electrode, and take the third reading. So now we have the three results taken across the resistance curve of the soil. We calculate the mean average, or let the Chauvin Arnoux do it for you to give you your mean average earth resistance readings. But here's a question that baffled me. Why is it 62% for the potential probe? I always thought it was halfway. I mean, Guidance Note 3 and the on-site guide both say that you put the potential probe halfway between the current probe and the electrode under test. Well, when we inject current into the ground, it does not travel in a straight line. It spreads out through the soil. That creates an area of influence around the earth electrode under test, and it also creates an area of influence around the current probe. If we place the potential probe too close to either of those, the readings will be affected. We are no longer measuring just the electrode. We are measuring the interaction between the two. In a simple uniform soil model, something interesting happens. If you plot resistance against distance between the electrode and the potential probe, the values rise and flatten out and then rise again. That flat section is where the influence of the current probe is minimal, and mathematically that flat point sits at around 62% of the distance between the earth electrode and the current probe, and that is why it's 62%. So now we're going to move on to earth fault loop impedance testing, or loop. Earth fault loop impedance testing answers a different question to earth electrode resistance testing. Earth electrode testing tells us how well it's connected to the ground. Loop testing tells us that the fault path is complete and good enough, so that the protective device will operate in time. On a TT system, that fault path can be long. It includes the line conductor, the protective conductor, the earthing conductor, the earth electrode at the installation, the earth electrode at the source, and the soil in between. So the earth fault loop impedance values on a TT system will always be higher than on a TN system, and that is to be expected. It isn't about how low the numbers are, but whether those protective devices will operate in time. On TT systems, BS7671 does not give a single maximum ZE value in the same way it does for TN systems. Instead, the maximum permitted earth fault loop impedance depends on the protective device being used. In most TT installations, fault protection is provided by a time-delayed Type S RCD, and BS7671 sets the requirement that the product of earth resistance and the RCD operating current must not allow the touch voltage to exceed 50 volts. And this is why TT systems can tolerate much higher loop values than a TN system. To put that into context, for a circuit protected by a 30 mA RCD, BS7671 permits an earth fault loop impedance of up to 1,667 ohms. There is one number that you may often hear mentioned on TT systems, and that's 21 ohms. So what is it, and is that the maximum permitted ZE for a TT system? Well, no. That figure relates to the distributor's earth at the supply transformer. It is not a requirement of your installation. Now, I didn't know this because I thought 21 ohms was the maximum ZE for a TT. But what about the maximum permitted value allowed for earth electrode resistance testing? Again, a number you may have heard of is 200 ohms. And that is right, because anything above 200 ohms is considered unstable. What we're after is a low stable reading, and soil conditions can affect those readings dramatically. Frost, snow, wet weather, all of these will impact the resistance of an earth electrode in the soil. And we are going to be finding out how these conditions affect earth electrode resistance test readings in the next video. But there is one more thing you need to be careful of when you're doing earth electrode resistance testing, and that is parallel paths. But all of that's to come in the next video, including how we tested the resistivity of this 100 square metre patch of field in the East Riding of Yorkshire. Click the video on screen to find out how.